mileage out of this. This is the basis for some other things we'll talk about later. So first of all, what's a rational function? Real quick review from yesterday. How do we define a rational function? Ratio of polynomials. Good. And you told me yesterday correctly that, so if we have a rational function, where would we expect to find vertical asymptotes?
Q of x is 0, C of x is not.
Okay, good. At values of x that are zeros of the bottom but not the top, we would get zeros of the function, x-intercepts, where?
P of x is 0, Q of x is not.
Good. P of x has a 0 and Q of x does not, and holes would be zeros of both. Good. Okay? So that deals with a lot of the behavior, but then the next issue is, let's talk about the end behavior of rational functions. We looked at one example yesterday. We took an example which you were able to generalize. We took an example where we had a second order polynomial on the top and a third order polynomial on the bottom. And when we took the limit of this as x approached infinity, we got, right? And how are we able to generalize that? When would we expect, if we take the limit of a rational function, that we're going to get 0 as a result? Okay, good. Bottom's higher order than the top. Let's pause and think about that for a second, because I want to make sure that you internalize the theory behind that too. So as x approaches infinity, what is the top approaching?
Infinity.
Infinity, yeah. What's the bottom approaching? Infinity, yeah. So is that a little weird that they both can approach infinity and yet the answer can be 0?
Bottom.
Yeah, the bottom ones, and it's hard to say that talking about infinity, you know, we could spend a whole year just having the math of infinity and we wouldn't cover it all. Infinity is infinity, right? But the rate at which you grow to infinity is what's important here. Which one is growing faster, the bottom or the top?
Bottom.
Okay, as x approaches infinity, how much faster is the bottom growing than the top?
More.
Substantially, in fact, infinitely, right? As x approaches infinity, the bottom begins to grow infinitely faster than the top. So even though the top is going to infinity, is dwarfed by the bottom, which is getting there infinitely faster, right? And so at any one snapshot in that film, think about that video of the top growing compared to the bottom growing, they're both going to infinity, but at any frame in that movie, as we watch this thing grow, as x gets infinitely far out there, well, the bottom is growing infinitely faster, and so that's going to push this ratio to 0, right? Okay, so we did the math associated with that, and that was no big deal. You know, all we did was, quick review, we factored out something that we could cancel from the top and the bottom, factored out an x cubed, canceled it, and then we were left with, when we did that, we were left with, in the limit, x goes to infinity, 0 over some number, which goes to 0, right? Which is 0. But the important thing for you guys is just to remember that that's a pattern. When the bottom is bigger than the top and it's a rational function, the limit goes to 0. Let's look at a different case. Let's look at something like, how about this? Oh, by the way, one other thing, in this last one, before we jump up there. What if I had made this a negative infinity? Would it have changed anything? It wouldn't, would it? If I had made this, if I had gone through the whole process of making this a negative infinity, all that would have happened is, well, nothing. Wouldn't have changed anything, would it? Right? Because in the end, plus or minus infinity on the bottom is going to make this fraction go to 0, right? If this were to be a negative infinity, it just would have been a 0 minus. No big deal. It's still approaching 0, right? You see what I'm saying? So it doesn't make any difference. So we can safely say plus or minus infinity, and we're going to get back the same answer. Let's look at really quick, I guess one thing that might be helpful. Let's look at a graph of this. So here is a graph of that function that we just graphed. Right, there it is. So as I zoom in, it looks pretty bizarre, right? The behavior, the near field behavior, the near end behavior, right? Not talking about excluding the ends, can be bizarre. It could be anything. But when we pan out, look what clearly happens. We don't even have to go out that far, and we can see that there's pretty obviously a horizontal asymptote that extends to negative and positive infinity. Both ends share the same asymptote, which is y equals 0, or f of x equals 0, right? Which is what we just proved. Okay? So let's look at something like this. And I'm going to go ahead and make this, instead of just choosing a negative infinity, let's just make it a plus or a minus. What do you think is going to happen here? Remember this from last year? What do you think? What's that limit going to equal? 5 halves, yeah. You can see what the math's going to be if you kind of just think ahead a little bit. If I wanted, what could I factor out if I wanted to prove that it's 5 halves?
X²
I could factor out an x squared, right? So I could rewrite this if I wanted to as the limit of x squared over x squared. And on the top, if I factor out the x squared, don't I just get 5 minus 3 over x plus 1 over x squared? On the bottom, I'd get 2 minus 37 over x squared. I could vertically cancel the x squareds to eliminate the indeterminacy. And I said indeterminacy. We're used to that being 0 over 0, right? That's what we always did. When we did our limit stuff earlier in the year, we only had 3 outcomes. We either got an answer or a number that could be 0, but it didn't have a 0 on the bottom. We got a number on the top and a 0 on the bottom, which was no limit. And then later on, we were able to decide, if we did one-sided limits, we could even determine is it approaching positive infinity from the left or negative infinity from the left, etc. Or we got 0 over 0, which always meant what? What do we always say? If we get 0 over 0, that means more work, right? We had to do something to eliminate the indeterminacy. Well, in this case, we're getting infinity over infinity, right? That's also indeterminate. That's an equally indeterminate form. There are a bunch of indeterminate forms in math that we have to resolve mathematically. We've only dealt with, to this point, 0 over 0, but now we're dealing with an infinity over infinity, right? And we eliminate the indeterminacy same way, by canceling the factors. When I cancel the factors, in the limit that x goes to plus or minus infinity, what's happening to these 3 terms? They're going to 0. And so we end up with 5 halves. Right? Okay. Okay, so why do they go to 0? Let's just take one of these as an example. Let's just take this guy right here. The limit of negative 3 over x as x approaches plus or minus infinity. So if I take that limit, what am I going to get? What if we just put the negative with the 3? I'm going to get negative 3 over, let's take the plus infinity, how about? Instead of, getting this up a little bit. We'll just take one of these, but it would work equally well for the other one. You'll see that. If I approach positive infinity, I get negative 3 over positive infinity. Well, what's that equal to?
0.
Yeah, does that make sense? If I have a finite numerator and the bottom blows up infinitely big, what's that doing to the fraction? Well, in the limit,
Infinitely small.
it's making it really small, isn't it? Right? Think about the progression here. Let's look at Desmos. If I take, how can I do this easily in Desmos? Well, I'll just graph that function. What if we take, let's just take the function, that's the wrong one. Oops, this one. So if I take -3 over x, and let's zoom in. So there's -3 over x. As x approaches infinity, look what this function is doing. It's getting closer and closer and closer to 0, right? As x approaches negative infinity, what's it doing? It's getting closer and closer and closer to 0. And I don't have to go out very far before this looks pretty much exactly like 0, right? If I want to pick a point, like what if I pick that point right there? The coordinates are -175.4, 0.017. If I go even further out and I pick a point, well, it doesn't even, it just says 0. It's not 0, but to within as many places as Desmos calculates, it's 0, right? It is a small decimal. You see the point, though? If we take a function like this, where we have some power of x on the bottom and a constant on the top, the bottom, as we go infinitely far out to the sides, right? As x grows either positive or negative direction, it doesn't matter. The bottom is going to get increasingly big, and the fraction gets pushed down and down and down towards its limit of 0. Okay? That makes sense? Okay. So what's a general rule then? What could generalize this example? It's one example, but it's exemplary of a whole category of rational functions. If we take the rational function, the limit of a rational function, what's special about this one? The orders are the same. Good. Top and bottom, same order. Then we just take the ratio of the leading coefficients. That's it, right? So the limit is always just going to equal that, right? Make sense? By the way, this syncs up with the conversation we had earlier in the year. Remember we talked about remember the day I put up an example on Desmos. It was, I think it was like a 4th degree polynomial, and when we looked really close, it looked constant, and then we panned out, it looked linear, we panned out, it looked, remember that, it looked quadratic? You remember that? Did I not do that? Really?
Yeah.
Oh, well, let's do that. It's kind of fun. So I'm going to make up a function here. Let's say I'm just making this up on the spot, so it may not work quite as well, but I think it'll work. Okay, let's try this. Are you sure I didn't do this? So if we look really closely, that looks linear, doesn't it? Right? If I start to pan out, there's going to be a point where it starts to tweak it just a little bit here. There we go. That'll do the trick. Starts to look quadratic, doesn't it? Especially if I tweak one of these axes just a little bit. What if I do? Starts to look quadratic, doesn't it? If I go out a little bit further, oh shoot, I kind of blew it here, hang on. Put one more 0 in there. There we go. Starts to look cubic, right? Agreed? And if I keep panning out, eventually it starts to look pretty clearly quartic, right? And if I go far enough out there, let me just change the axes just a little bit here. Let's make x go from negative 1,000, or about 100. Oops, wrong one. What was that?
It was like negative 5,000.
Okay, close enough. Let's let this one go negative. Okay, let's try that. Then we'll do. Okay, that'll work. What's it starting to look like?
Icicle.
Icicle, true. There's a lot of work to prove a point, but it's a cool point. So that's looking pretty clearly like a quartic, isn't it? I mean, if I compare that to let's just compare that to the function g of x, equals x to the 4th. Well, it's a lot. I mean, let me make it just the leading term, 0.1234561. Look at that. They look almost identical, don't they? Right? Okay, so what's the moral of that story? Moral of the story just is that when we look at this function, when we go on a very large scale, which of those terms dominates the behavior of the function? The highest order one, yeah, the biggest power of x, right? And so even though close to home, these other ones appear to be dominant, when you get really big values of x and you zoom out, the leading term is the one that's dominant, right? And that's the way it always is with a polynomial. So if we use that line of thinking, we can go back and even approach this from another angle. We go back and say, okay, well, if we want to look at this limit, it really should just be the leading terms is all that matters, right? When we're taking the limit of the function. Right? So if we take the limit of 2x squared over 3x cubed, if I reduce that, that just ends up being the limit of 2 over 3x, right? As x, I look like an x approaches plus or minus infinity, well, that's pretty obviously going to be 0, isn't it? Right? All we care, the leading terms are all that matter. If we go to this one right here, the leading terms, if I look at the leading terms, if I take the limit of that, well, the x squareds are just going to cancel, right? And so it makes sense that it's just 5/2. There's all these different ways of kind of putting this together, but they're all completely consistent. That's one of the great things about math. It's so fascinating, is it all comes together. So then the other example would be something like this. What if we had the limit of some function? How about if we do 2x cubed minus, actually, 3x squared plus 1 over 4x squared plus x plus 3. Okay, how's that? And let's take these limits one at a time. Let's take the limit as x approaches infinity, for example. Okay, what's happening this time? What's going on with this? What's different about this rational function than the first two? Okay, top's the highest order. So what do you expect to happen then? Is this going to have a horizontal asymptote? If we look at this, the first one we already looked at, what if we look at this one on Desmos? Oops. Can I undo that? Yeah, I can. Good. So if we go in, so let me, what is this one again? Oh, darn it. It's 5x squared minus 3x plus 1 all divided by 2x squared minus 37. 2x squared minus 37. Okay, we get, and let's zoom in. Okay, we get that, right? And one of the things we're going to do with this are, I don't know if we'll get to this today or not, but our next step with the rational functions is, in these limits, we're going to work on building tables, because we have most of the tools required to do a sketch of these things. One of the very few things we were lacking was just the ability to put the end behavior in, right? And that's really what we're adding. And now we can add the finishing touches to our tables so we can get everything on these tables. So we can see that close to home, close to the origin, it's crazy behavior. But as I zoom out, what do you see? There's a horizontal asymptote at what y value?
5/2.
5/2, right? 2.5. As we get further out there, it's trying to get there, right? So both of those first two examples did have horizontal asymptotes. First one was at 0, second one was at 5/2. What about this one? Is that going to have a horizontal asymptote?
No.
It's not, right? If we take the limit as x approaches infinity, let's just kind of think about this in terms of looking at the dominant terms here. What's the large scale behavior going to be? This is equal to the limit of the leading terms, right? As x approaches infinity, because they're all that matter. So limit of 2x cubed over 4x squared. And what's that reduced to? X over 2? Well, what's that in the limit? It's the limit of x over 2. What is that in the limit as x approaches infinity? Infinity. So that's a no limit kind, isn't it? Right? What about as we approach negative infinity? The limit of that whole thing. As x approaches negative infinity, aren't I just going to get, I'm going to get x over 2 as x approaches negative infinity. That's just going to be negative infinity, right? But we can see that on Desmos. Oops. There we go. There we go. So let me put that in real quick. So we got 2x cubed minus 3x squared plus 1 over 4x squared. Okay, that. Okay, so there's our function. We can see that it ramps up to infinity on the right, down to negative infinity on the left, right, if we go out there very far, okay? But is there something more interesting that we can say about this?
Bigger.
Can we describe how it's gonna go to infinity? What happens if we divide this out? Let's take this rational function, let's call it r of x, and let's divide it out and see what we get. So this what's that equal to? Okay, this is good review, by the way. How do we go about dividing polynomials like that? Can we use synthetic division on that? Give me a thumbs up, thumbs down. Okay, so we need a little review on this, don't we? Okay, so I like this about calculus. We get to review all the important stuff. So synthetic division only works if the bottom is linear, right? Bottom is not linear here, so we have to use polynomial long division on this. I think one example is all it'll take to get you back on track with this, but how does this work? So if I want to set up my division template here, it's going to be long division. What goes where? Okay, so the 4x squared plus x plus 3 goes outside because that's dividing into 2x cubed, blah, 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 right? So outside we've got a 4x squared plus x plus 3. Okay, it is not necessary to preserve all of the powers of x on the outside. You don't have to, like, let's say we just had 4x squared plus 3. I could just write that as 4x squared plus 3. That's fine. But on the inside, if I'm missing a power of x, I have to use a zero coefficient. You don't technically have to, but it's a terrible idea not to because the math gets really messy, right? You always want to leave a column for every power of x. So this top one's going to look like 2x cubed minus 3x squared plus 0x plus 1, right? That's all looking familiar? And then, I probably picked kind of a bad one here to do. Pretty sure I did pick a pretty bad one to do. Well, that's all right. We can do it. We'll do it anyway. Okay, so how do I know what goes here? Okay, good. You're right. You're on the right track. So we're going to ask how many times does the leading term of the denominator divide into the leading term of the numerator, right? And so we'll just do a little division problem here. We'll just say 2x cubed divided by 4x squared equals what? Okay, so I'm going to get a 1/2 x, right? Everybody agree? So up here then, we're going to put a 1/2 x. Okay, and then anytime a number appears on the top, we're just like in regular long division, we're just going to distribute that through and subtract, right? So what do we get if we multiply the 1/2 x through our denominator? 1/2 x times 4x squared, of course, gives us our 2x cubed. It has to because we're going to subtract those. 1/2 x times x gives us a 1/2 x squared, and 1/2 x times 3 gives us 3/2 x. I apologize for picking one with fractions. I wasn't really thinking ahead there. I should have picked one without fractions, but that's all right, I suppose, huh? So then we're going to do this. I urge you to do this. Put this in parentheses and subtract the whole thing. So when you get in the habit of doing polynomial division, the pattern is this. You always go top minus corresponding term. Top minus corresponding term. Then you don't make sign errors. Okay? So this is going to cancel like it has to. Negative 3x squared minus 1/2 x squared is how many x squares? Negative 3.5, which we'll write as 7/2. And then 0 minus 3/2 is negative 3/2 x and we'll drop down to 1. So then we have one more term to go, don't we? We've got 4x squared divides into negative 7/2 x squared. How many times? Well, we can see. So negative 7/2 x squared divided by 4x squared. Well, the x squareds cancel, right? And negative 7/2 divided by 4 over 1 is the same as negative 7/2 times 1/4, right? So negative 7/8. So our next term is negative 7/8. And we'll distribute that through. And what do we get if I distribute that through? Negative 7/8 times 4 would be, what is that? It's negative 7/2. Oh, it has to be, duh. Negative 7/2 x squared. Negative 7/8 times 1, that's easy. Negative 7/8 x. And negative 7/8 times 3 is negative 21/8. And I'm going to subtract the whole thing. Those go away. Negative 3/2 x minus negative is plus 7/8. So what's that going to be? Negative 6/8 plus 7/8 is just 1/8, right? So I'm going to get 1/8 x and then 1 minus negative, so plus 21/8, 29/8. Yeah. And that's my remainder, right? Because now x squared will no longer divide into that, right? And so we can say that if we go up here, I have to get rid of this. So now we can answer our question. What did this equal? This equaled 1/2 x minus 7/8 plus the remainder 1/8 x plus 29/8 divided by, yeah, it remains over that. Yes, sir.
Why is that not negative 5/8?
Is it
Is it, did I screw up?
for 1/8 x, yeah?
Oh,
Because 3
what should it be?
negative 5/8.
Oh, yeah, what was I doing? What the heck was I doing? I don't know what I was doing there. I was thinking 3/4. I don't know what I was doing. So it should be, you're telling me, you're right. That should be negative 5/8 x. Okay, that's good. So then I gotta change it up here too. Oops. All divided by this. Right, so all we did, now let's just, that's a lot of work, but let's just backtrack and see what we did. We just rewrote our original rational function. We divided it out. We wrote it as a polynomial plus some remainder, plus some rational function that we had a remainder divided by x squared. Let's take this function, the quotient after we've divided it, and let's take that limit. Okay, so what is the limit of this whole thing as x approaches plus or minus infinity? Well, we can see that we're going to get plus or minus infinity, but more importantly, what's going to happen to these terms? As x approaches plus or minus infinity, this one's going to grow really big, right? This one is constant. What happens to that term? Goes to 0. Yeah, that term goes to 0. And so what we're left with, the only terms that don't go to 0 are 1/2 x minus 7/8. What does that look like? What kind of function is that? Yeah, that's linear, isn't it? Let's just see what happens if we plot that line alongside our function. Okay, so we'll call this g of x, and it equals 1/2 x minus 7/8. Okay, so there it is. Green function is the rational function. The orange function is the linear function that we got when we took the limit, right? When we divided it out and took the limit. So if we start close to home, they don't look very similar, right? But as I pan out, what's going to happen? They look identical, right? So what is that orange function? It's guiding the large-scale behavior of our green function, right? As we go further and further out, the green function is sticking to that orange function. What does that sound like? What's that sound? What kind of tool in math does that? Say it louder.
A derivative.
Well, it's not really what I'm looking for. If we go back and we look at like our asymptote. Yeah, right, that's an asymptote, isn't it? That's what asymptotes do. When we go far out to the sides, the asymptote is what the function sticks to, and so it guides the large term behavior. What we're going to end up doing when we sketch our functions, a lot of times you can think about the asymptotes as kind of forming the skeleton of the function, and the function just has to stick to those bones, right? So if you knew, for example, what if I knew that I had a function whose asymptotes did this? Let's say that our asymptotes were these. I had a horizontal asymptote here, and I had vertical asymptotes there and there. Pretty much tells you what this function's going to do, right? I mean, it might do some funky stuff in between, but on a large scale, there's only a few possibilities, right? What's the only thing that could happen to the left of this asymptote? There's two possibilities on a large scale. Yeah, either it's going to do that, or it's going to do that, right? For sure. Same thing over here. It's only got a couple possibilities. It's either that or that. Now, in between, there's a few more possibilities, right? It could do that, or it could do that, or it could do something like that, right? But you get the idea. I mean, once you know where those asymptotes are, that kind of tells you on a large scale what this thing's going to look like. And then we'll just use our table to find out the little nuances in between. Yeah?
How could that last green one work?
Does that just mean there's not a point on that?
The green one?
Yeah.
You mean because it passes through this asymptote? That's fine. You can pass through a horizontal asymptote. All the horizontal asymptote tells us is just that it's at the ends, that's what it's doing. The horizontal asymptote has no meaning in here, right? What if I did the function, so just to prove you can pass through a horizontal asymptote, what if we did this one? What if we did the sine x over x? Sine x over x as x approaches infinity. What's that going to do? Well, as when x is positive, the bottom is always positive, isn't it? But the top is going to oscillate between positive and negative. So you kind of get an idea what this is going to do, right? It's going to go from something like, just going to do that in both directions, right? It passes through, what's the asymptote here? Horizontal asymptote. It's at 0, isn't it, right? Why is it at 0? I mean, this is kind of a topic for probably another day, but we can just leave off on this. Why is the limit of this function equal to 0?
X on the bottom is 0. Or, it's undefined.
Yeah, what are we going to, on the bottom is getting infinitely big. What's the top doing? Yeah, it's just oscillating between fixed values. Even though it's not constant, it's still trapped between -1 and 1, right? And so if the top is trapped between these finite values, but the bottom is growing infinitely big, we still end up getting 0, don't we? Right? we don't get a constant over infinity, but we get some trapped number. That's what we call it, say in math, it's trapped value, right? That make sense? Okay. I just love this stuff. I mean, it's just kind of, we'll go in. I mean, I've been just trying to kind of give you the theoretical background. We'll go in and nail this down with some practice problems too. But I just want you to see how all the, kind of what the large term behavior is and why it is the way it is. So maybe one more day and then I'll put the assignment up.